The number 2. Ta-da! It's probably the second number you've ever heard about. It's actually my favorite number, and I'm sure you like it too. What? You don't like it? Well, here's a reminder of how cool the number actually is. 2 plus 2 equals 2 times 2 equals 2 squared. They're all the same. 2 distinct points determine a line. 2 biological genders, X and Y, determine most species. Species of animals? Well, there are species of bacteria. Most functions we analyze regularly are two-dimensional, X and Y. Again, every even number by definition is a multiple of 2. 2 is the smallest prime.
1 isn't actually prime.
2 is the only even prime.
Which would make it the oddest prime?
Since it is prime, there are only 2 divisors. 2 factorial equals 2 times 1, which is 2. The infinite sum of all natural number reciprocal powers of 2 is 2. The Sith philosophy that states there can only be 2. Now, a number that you're probably familiar with is the square root of 2. And you may even know it as this. But what is it exactly? Okay, but why is it called the square root? So, I know you're an exponent expert because you watched this other awesome video. You know, exponents, repeated multiplication, such as... For the second power of any number, that's the same thing as multiplying it by itself twice. Raising it to the 2th power. This is called squaring because of this formula that gives us the area of a square. Ah. The inverse operation, or like the opposite of squaring, is called the square root. Like we're finding the root of the problem. If you ever have any difficulties trying to solve one of these, I always ask myself, what number squared equals this number? Don't forget the plus and minus. Yes, the square root of 2 is fantastic, and not just because it's the second root of 2. So 2 2's again, but it was actually the first irrational number to ever be discovered. No, it wasn't the second irrational number to ever be discovered.
Back in the day, like during the ancient Greek times, they believed that all numbers were purely rational, or rather, they could only be expressed in fraction form.
That's it. They only believed in fractions. To them, those were the only numbers that existed.
While everyone was happy living in fraction land, good old Pythagoras and his nerd buddies were studying really cool stuff like a squared plus b squared equals c squared, or how they knew it. In right-angled triangles, the square on the side subtending the right angle is equal to the squares on the sides containing the right angle. They will be immortalized as the people who generalized this concept, known for several millennia, and even named the theorem after Pythagoras himself, when they ran into a problem. Looking at the isosceles right triangle, square root of 2 shows up and it didn't quite fit the description of a fraction. The story goes that one of the Pythagoreans insisted this was true, that this number transcends their original belief of how a number was defined. Pythagoras was understandably upset. He did the only rational thing you would do in this scenario and
took him out on a boat and forced him to drown. Nevertheless, research into non-fraction numbers was quickly put into motion, and because of this discovery, square root of 2 is sometimes referred to as the Pythagorean constant. There's actually a really neat application that comes from the 1-1 square root of 2 ratio coming from the 45-45-90 right triangle.
time travel. When you move around in real life, if you want to walk forward, you travel one step. And if you want to walk diagonally relative to your line of sight, you would turn 45 degrees and then take a step. Here, 1 step is your unit of walking distance. You can actually visualize a circle with radius 1 step around you at all times. All steps will be the exact same distance, and we can even be as bold to say that it's the same distance covered per unit time. This is the definition of speed. With me so far? When you move around in video games,
Yeah, we're going there.
sometimes they'll program the game to simulate this authentic walking experience, where you turn on your own axis and then move forward. But if you play certain games, you can straight up destroy a consistent universe. To explain this better, let's have one of the most complicated games ever created aid us in our quest. Don't worry, we'll only need to use the basic movements of these 2 pieces, a bishop and a rook. The rook can move up, down, left, or right, as many spaces across the board in a single turn. The bishop can move in any diagonal direction, again, as many spaces as it wants. Here are some sample moves these pieces can take. Well, to fill up the dead space, and in case you were wondering, I have no knowledge of competitive chess strategy. I know how the pieces move, what the words checkmate and check mean, how to leave Ron Weasley behind after he gets knocked off of his knight's horse, and the castle maneuver. That's about it. I enjoy the show, but I have no idea what the Queen's Gambit actually is. Do they ever explain that? I'm only 2 episodes in. But after trying different models to explain the concept at hand, I figured this was the best one to use. Ultimately, we're going to find the ratio of how far they travel, and to get the best idea of what that ratio is, we're going to maximize the movements of these pieces, having them make the longest journey they can across the board. Then, using a measuring tape, we can find a suitable approximation of the distances covered.
No!
The rook seems to travel about 22.5 centimeters. We're measuring from the middle of the squares because that's where the pieces rest in between moves. Rather than trying to find an analog of the edge of the starting square, it's a great rotation point to find the diagonal length, which comes to about 31.5 centimeters. This means that even if the pieces move the same amount of spaces according to their own relative restrictions, the bishop actually moves a greater distance in a player's turn compared to the rook. But by how much? The ratio of the distances we measured is exactly 1.4, and well, that's to be expected. But what does this have to do with video games? Well, when you play a game that features a strafe mode, you can think of it as the character looking through the eyes of a rook. One joystick controls your up, down, left, and right walking movements, but your looking direction doesn't change. See, you're not rotating, even though you're moving side to side. If we come across a game in which you can strafe, that happens to have a square grid layout like this, rather than the circle layout like before, if we were to take a diagonal step when strafing, we would be going to the next diagonal square on the grid. We're moving like a bishop, even though our orientation has us believing we're a rook. We would have a speed boost factor of the square root of 2, moving about 41% faster in the same unit of time. In other words, time travel. But before you go out and try to pull a fast one on your friends... Oh my god, you're gonna take forever, aren't you? Okay, good. Video game makers have figured this one out for a while, and to keep it fair amongst the player base, they've programmed modern games to compensate for this discrepancy.
Ooh.
But for video games old enough, this Pythagorean shuffle is actually a well-known trick with video game speedrunners.
Ah. Huh.
I even tried it out myself with a few games.
Oh my god, go away. Can't you see I'm running an experiment here?
Alert! We need to keep moving. Get back in the Warthog.
And I had to go all the way back to Bethesda's The Elder Scrolls 3 Morrowind
Oh my goodness, please move. Thank you.
before I had any success.
Oh, don't you dare. Ugh. Who are you? Ah! That's just terrifying.
A person died to allow us to walk in video games just a little bit faster.
Alert! We need to keep moving. Get back in the Warthog.
I can't. I'm dead.
Thanks for watching.
Oh no, wait, I want to talk about binary.
Ow.